In this video, we will do an RI-CC2 calculations, which is a UV or one-photon absorption calculation or vertical excitation calculations. We're going to get the excitation energies, oscillator strength, transition moments from this calculation. We are selecting the resolution of identity, which is implemented in TURBOMOLE. Resolution of identity speeds up the calculations by approximating the two-electron integral, and CC2 is an approximated singles and doubles coupled cluster method, which is an accurate method. So in TURBOMOLE, basically, you have a project. I believe when you open up the, I believe you've already set up the project when doing this. So you have a project, which is basically your folder where the other folders or files will be. And then we start by doing a new job. We're using the GUI here in order to prepare the input file. But in order to perform the calculations, I highly recommend using the terminal. It's just a lot better to perform your calculations. That is, of course, if you want to just run it on your own computer. If you don't, then you can basically just run it on a cluster, which is something we will do later on. We import the coordinate file, and the best thing to do is just to convert your optimized geometry into an XYZ file, and then just open it. Now, this we do only when we have an optimized geometry from another software. For example, we've optimized a geometry using Orca or using Gaussian, and we want to use that same optimized geometry into TURBOMOLE. And in order to basically just get that, you change the coordinates into an XYZ file, and then you open them. In this case, I have the green fluorescent protein chromophore, the anionic chromophore. And when you open it up, you can simply check the molecule by looking at the 3D molecular builder herein. So we have the GFP anionic chromophore herein, just to double check. You can see it here. And you can do changes to the geometry herein. That's pretty easy by using building blocks, atoms, or just changing one of the coordinates by rotating them here. And when you do that, you click on close, and what happens is that the coordinates, they change immediately. One thing as well is to consider the symmetry when you do the calculations. We were neglecting the symmetry, so it was C1. When you auto detect the symmetry, we know that there is a CS symmetry for this molecule. And that actually matters when it comes to computing the properties, because C1 has a different irreducible representation compared to CS. And RI-CC2, you will get different results. Now, we click on continue, you can select the basis set. In this case, we're going to select def2 SVP. Not all basis sets implemented in TURBOMOLE are available in the GUI. This thing you need to keep in mind, because, for example, you want to use OGCCPVDZ, you would have to use the defined command in the terminal, which is why I recommend using the terminal anyway. But in this case, at least we can get a perspective looking into this, and we can absolutely change the basis sets manually by taking a look at the basis sets, the atoms included, involved in the calculations, and of course using basis set exchange to get the basis sets for the atoms we have. So we have def2 SVP. We click on continue. I know you need to specify the molecular charge, and this is quite easy when it comes to TURBOMOLE. I know that the charge of the molecule is -1, so it is -1. We'll click on generate molecular orbitals, and it's simply specified as a singlet for the multiplicity, so it's -1 and 1. It's a restricted calculation. It will be, since we have a singlet multiplicity, and it specifies the molecular orbitals given, which are basically, they're a guess. The molecular orbitals here are a guess. A Huckel guess is used to generate the molecular orbitals, and of course the calculations builds up on that. When you do the calculations, you will find that the first step is doing a direct SCF, generates. So it takes that initial guess and iterates on it for the SCF, and it generates new molecular orbitals for you, so that you can proceed with the calculations when you do RI-CC2. So we click on continue. It says here use RI, but we have DFT. Of course, you can unclick it. Let's click back and select CC2. We want to freeze the molecular, or we freeze some of the molecular orbitals. What happens in order to use CC, we freeze the intercore, we use the, we freeze the inner core molecular orbitals, and they're basically, technically, they're not involved in chemical bonding or reactions. They're tightly bound to the nucleus. They're close by to the nucleus. They don't contribute significantly. They don't contribute significantly to the dynamic correlation part. So we can basically just freeze them. They're not included in our calculations. These are the inner ones. Okay, so we've done that for the CC2. We're using, so by default, TURBOMOLE uses the auxiliary basis set, similar to the basis sets that you select when you use the GUI. And that also happens when you use the terminal as well. We click on continue. Here, it's actually here the job type is geometry, ground state geometry optimization, but what we're looking into is single point energy calculation, getting the vertical excitation, which is basically similar to going to spectra UV-Vis. They're basically the same. We want all irreducible. You can select all irreducible representations since we're using the CS, or you can select a type of irreducible representations. It could be A prime or A double prime, depends on what you want to do. In this case, we're just going to select all irreducible representations, the A prime and A double prime. And we want two singlet excited states. So we're taking the first two singlet excited states. Of course, you can change them into a triplet, but we're interested in the singlet ones. You can just save your input file, which we will save on the project where you've already made the project for TURBOMOLE. Excuse me. So it goes on. We go on saving it, and when you save the file, you go back to the file. You'll find a number of files. They're basically the auxiliary basis set, the basis set control, which is your input file, and the coordinates, and we need all of them. You already have your molecular orbitals as well. But what you can do basically is just remove the molecular orbitals. If you want to just write your own basis sets, you can remove the molecular orbitals and just change them however you want by changing the basis set, I mean, without needing to provide an MO guess, because basically you're going to use the DSCF to generate molecular orbitals. Just make sure when you do that, the control file itself doesn't have the molecular orbitals file already written into the input control file, because if you don't do that, the calculations will crash. So you've got the input file, and of course you can run locally your calculations. You can run it, or you can run it on a network, or you can save it and just transfer it to your cluster and do the calculations, or just use the terminal. Now let's jump into using the terminal, which is for the second video.